Welcome to the next recording session, and I intend to cover the remaining portion of whatever is in the chapter that we call filters. Well, actually, in the textbook, there's two chapters. There's chapter 14, which is passive filters, and chapter 15, which is active filters. Now, as I had said in the beginning, I don't really want to spend too much time on active filters, but I think it might benefit you to at least have some idea what they are and why we study them separately. So I will try and at least introduce active filters also to you in this recording. Okay. So this will be mostly a theory, a lecture recording, and the next one I will do some problems on this material. Okay, so until now we have covered um, high pass and low pass filters, which were first order RC or RL type circuits, and through the various connections of the RL and RC, and how we define the output terminals, you were able to see that the same basic circuit could function as a high pass, has a low pass, or a high pass, right? And then we also did some problems where we identified, there were a bunch of formulas that we found that are given to us in the textbook, and the problems essentially were, okay, use these formulas to find the corner frequency, to find an expression for the transfer function, and then, if you have different frequencies for applied to the input voltage, that means if the input voltage is a sinusoid and takes different frequencies, then obviously the job of the filter is to pass some of them with full magnitude and the others to cut them off or reduce them in magnitude to a very small quantity. Okay, and that's how we saw that the problems helped us to understand in reality with real numbers assigned to resistances and capacitances and inductances how we can create different ranges of frequencies that are either allowed through the circuit or stopped. Okay, so that was your first set of lessons on filters, and let's move on to the next one. So we have two other filter types just in the passive filter chapter that we will cover, and of course I've shown you briefly what these are. These are called band filters, band pass or band stop, and they have many other names, but the band filters, they have they operate on both sides. So what I mean by that, we'll look in some detail starting with this slide that I have, and this is slide number 19 that I have open. So I hope everyone is looking at slide number 19 on the lecture PPT file. So what is a band pass filter? And this is section 14.4 in our textbook. So a band pass filter is designed to pass all frequencies within a band of frequencies. Okay, not too difficult to understand, but there is a definition, and that's the definition I found. So between a band, generally either shown to be a lower limit of omega 1 or omega C1, C meaning cutoff. So omega C1 or omega 1, some textbooks will use C1, some will just use 1. Similarly, on the high side, you have omega 2 or omega C2. Okay, so the range of frequencies between omega 1 and omega 2 is called the pass band, and then the remaining frequencies are all in the stop band. Okay, so the pass band, it has a width of omega 2 minus omega 1, and that width is called the bandwidth. Now, the big difference compared to the previous forms of filters we just studied, there in the previous forms we only had one cutoff frequency, right? Here, as you can see, there's two cutoff frequencies or two corner frequencies, omega 1 and omega 2 in this drawing. And then there's something in the middle also called center frequency, omega 0. And all three are important. They're used quite a bit in filter design and actually in solving problems. So you have to become familiar with them. Now the definitions of omega 1 and omega 2 are pretty much similar. That means the magnitude has to drop to 1 over root 2 or 0.7, and at that point we define it as a corner frequency. Okay, it's just we have 2 in this case. So looking to the left, I mean, we've seen the picture, the graphic. On the left, there's definitions of or introduction of the corner frequencies omega 1 and omega 2, center frequency omega 0. Oh, important thing to notice is omega 0 equals square root of omega 1 times omega 2. So this is a geometric mean, not an arithmetic mean. And I'm sure you know the difference. I mean, if omega 1 was 20 and omega 2 was 60, if it was a simple arithmetic mean, omega 0 would be right in the middle, right? So between 20 and 60, you would have 40. But if you calculate the geometric mean, it's not going to be 40. I think it's maybe 36 or something. But the formula uses geometric mean and not arithmetic mean. So just be careful in case you get a problem and you can't, make the mistake in calculation. Also, what else do we have on the left side? So at the center frequency, the magnitude of the transfer function will be the highest. The magnitude of the output will be the highest. And I also show you the band stop, that's in the next section. But with the band stop, it will be the opposite, it's 0. But for band pass, you notice that the magnitude of the transfer function h, if calculated at omega 0, you get h max, which is the maximum value. Most cases, we take that to be 1 for passive filters. Okay. Bandwidth is defined as omega 2 minus omega 1. So bandwidth is a new concept, right? I don't know if we called the previous cases bandwidth. No, I don't think we ever used the word bandwidth previously. So just remember now, you're introduced to a new term. Bandwidth is the width of the frequency range between omega 1 and omega 2. Okay? Lastly, to the rightmost, you notice that the transfer function, if written in S form, S domain, is beta S, and beta is the bandwidth. Sometimes beta is used, sometimes B is used for bandwidth, but bandwidth appears in the top, and then you have S pi S square plus beta S plus omega 0 square. Immediately you notice that this is a square equation, an equation in S square, and so you can guess that as we look to implement these circuits and achieve this bandwidth or this transfer function, this is going to be a circuit with two energy storage elements, right? Probably a C and an L, and of course an R. So RLC circuits. Okay. So that was the introducing you to a bandpass filter. Let's move to the next slide, slide 20. Oh, we have a new topic here. You guys thought we were in filters, so how come we have moved to resonance? Okay. Resonance is an important concept to understand before we understand and do a little more work on both band pass and band stop or band reject. the idea of resonance is introduced to students in a circuits course in many different situations. We could have done this earlier when we were doing sinusoidal response. In fact, I remember quite clearly when you guys did some lab projects, remember, for EE188L lab, many teams picked up on the resonance topic to do a demo, right, to do a presentation. So I'm sure you're already familiar with resonance. Some of you may have read about it, I mean, somehow you have heard about it. So let's do a little more into resonance, because this is, now we can't avoid it. At this point, to understand the remaining filters, we have to have a little more understanding of resonance. So I will introduce resonance. I don't really want to, you know, uh, make you do any problems, etc. The idea is not too difficult. I'm sure you can do the problems if necessary, but let's just say I won't give you resonance problems for homework or in the exam. But when we do actual problems on filters, bandpass filters or bandstop, the same concepts are applied. So with that, let me introduce you to the idea of resonance. So in this slide, there's nothing, it's just a definition. What is the definition? Resonance is a condition in an RLC circuit. So it's an RLC circuit. So you got to have both L and C along with an R, in which the capacitive and inductive reactances are equal in magnitude, thereby resulting in a purely resistive impedance. Okay, so that's the basic definition, and of course we look at it a little more, but just try to remember that fundamentally you have something that's going to be equal in value, and that's capacitive and inductive reactances equal only in magnitude. Phase, they are automatically out of phase by 90 degrees. I'm sure you know that. But the magnitude is what is important, and so if the magnitudes are also important, then what happens is the capacitive reactance and the inductive reactance kind of cancel out, and you are left with just resistance in the circuit. So that condition is called resonance, and it happens at a certain frequency. So it's tied to all this stuff that we've been studying in the last few sessions about frequency response. So it's part of the frequency response story. And so to understand resonance, you have to first know that we are discussing a situation where frequency is not fixed, which is what we assumed, all of our previous work, but frequency is shifting, can change. One input signal can go across many frequencies, or we could have one input signal which is a mix of many frequencies, right? So in either of these cases, it's possible that you run into a resonance situation, condition. Okay, so a little more on resonance. I'm going to move to slide 21, and more material here. A lot of it I just copied and pasted. So, I think that's the best way to learn in some instances. So nothing original from me, but I hope as we read this together, you get the picture. Okay, so first I'm introducing a series RLC circuit to you, which means you know that the next thing coming is a parallel RLC circuit, right? But for now, let's focus on the series RLC circuit and see how it helps us understand resonance. So I don't have too many details, but enough to tell you what's going on. So let's look at the circuit and the graphic on the right side. So on the top we have a simple RLC circuit, and I have changed I've introduced the frequency domain reactance values into the circuit. So there's j omega L for the L and 1 by j omega C for the C, or you can write that as minus j by omega C also. But in any case, that's capacitive reactance, and there's inductive reactance. And of course, the resistance, it's the same for any frequency. So the picture below, the graphic below, shows you that, and you can see that it's looking to be like a filter pictures that you have seen. But remember, we are only talking resonance, so don't bring in filters yet. In resonance, as the frequency increases of the input signal, the output rises to the highest point at omega 0. At a certain frequency called omega 0, the output value, which is just shown in this case as Vm by R. It's actually, we are measuring a current, right? So when we say output here, we are only saying what happens to the current. That's all in this section we are considering. And the current rises to the highest value at a certain frequency, omega 0, and that's called the resonant frequency. So why does that happen? The graph is nice. It tells you how it happens. Why? Okay, let's look at the two equations in the blue color on the top. So if you just look at the impedance in the circuit, the ohms value of the impedance, that formula is how you write it, right? R plus J something. And at a certain point, the imaginary portion of Z, the impedance, the imaginary portion, Im, meaning everything in the brackets, that, let's say we set that to 0. So what happens? All that's left is an R, right? Because everything else falls to 0. And when can that happen? Simple, omega L equals 1 by omega C. At that condition of omega, you end up with the situation where the imaginary part of Z, the J part of the impedance, just disappears and you're left with resistance. So since current, which is the output of interest here, is voltage by resistance and voltage by impedance, and impedance only has a resistance now, two things are going to happen. The current will be in phase with the voltage because it's only a resistive load, number one. Number two, any value of, whatever is in that brackets, the imaginary value, any additional value, anything more than 0, will add ohms to the circuit, right? And the ohms will only decrease the current. So the bottom line is, at a certain frequency, the resistance is the imaginary part disappears, and that happens when the inductive reactance equals the capacitive reactance, leaving only the resistance, and hence we have the maximum current, and the current is in phase with the voltage. And the value of and the resonance condition, you equate the two, and so you come up with a value for when this happens. The omega 0, it happens when its value in radians per second, remember this has to be radians per second, not hertz. In radians per second, it's 1 by root LC. Okay? Alright, so a few more points. I think there's 4 points I picked up from this textbook on resonance. Number 1, the impedance is purely resistive, so Z becomes R. The LC series combination acts like a short circuit and the entire voltage is across R. So all the input voltage at resonance comes out across the output resistor if you're interested in voltages. Okay, the magnitude of the transfer function is minimum at this point, and also point 4, the inductor voltage and capacitor voltage can be much higher than the source voltage. Now that's an interesting phenomenon, right? At a certain point, and this is the only situation in which this happens in a circuit with only passive elements. Passive elements are RLC. Generally, with an RLC circuit, the voltage anywhere can never be higher than the input voltage, but it can only happen at resonance. And so if you do the math, I'm not going to do it too much, but if you do the math, you'll find that you can get at resonance some extremely phenomenal output voltages, and sometimes these can damage. Sometimes they are helpful, sometimes they can be damaging, but it is possible to fine tune the circuit to get a real boom at that resonant frequency. Okay. So I hope these steps are, these points are clear. I can't say too much more, but let's move on to the next few slides. What do I have next? Okay, I have a parallel RLC circuit. Same ideas. In this case, though, the j omega L and the j omega C minus 1 by j omega C, they are also there, but they are in parallel, and again they cancel out under certain conditions, and you're left with just a resistance in the circuit. And at that point, the parallel combination acts like an open circuit. The entire current flows through R. There can be currents in L and C too, and they may even be higher than N, but they cancel each other out. So you're left with just current in the resistance, and it's in phase with the input current source. Okay. So same ideas, except here we plot on the graph on the bottom right, we are plotting for voltage across resistance as the point of interest rather than current, which is what we did in the previous case for the series resonant circuit. And so the voltage becomes the highest when at resonance, when the other resistances fall off, right? Now obviously many resistances in parallel, you know this, reduces the net resistance, right? So if other resistance disappear and there's only one resistance, the voltage across it is the highest when only that resistance stands by itself and the others don't exist. Okay, so that's the point that is being made here for the parallel resonant circuit, and everything else, the logic is pretty much similar. Okay, all right. Do I have any more on resonance? Okay, I have a nice summary here that was in the textbook. A different textbook, by the way. Don't get confused if you don't find this exactly. I know there's material on resonance in our textbook also, but it may be written slightly differently, but the ideas are the same. The summary of the characteristic of resonant circuits, you see everything we talked about. Some new things we have not talked about. The quality factor, Q, we haven't yet come to it, so we'll come there next. Don't worry yet. Bandwidth we talked about. There's actually a formula, nice formula there, but you need to know what Q is to understand why. Now you know what a bandwidth is, but it also has these formulas to help you find them in a real circuit. Also omega 1 and omega 2 you can calculate. So everything is written in terms of this Q, which is nothing but, you know, these factors, omega 0 into L by R, or R by omega 0 L, or omega 0 RC in a parallel circuit. So the same basic information, the RLC values are used, but they are used in different ways. There are many other formulas. There's not only one set of formulas. As you'll see as we do some more of this, you can either write these half power frequencies in terms of this Q, or you have formulas write directly using RL and C. So whichever is convenient, we can use those, and I'll show you those in a bit. One other thing, and at the end, Q is actually a quality factor. In some ways, the higher the Q, the better. And so if you have a high Q greater than 10 10, then apparently omega 1 and omega 2, you can do a quick short form using these formulas. Omega 0 plus or minus b by 2 gives you the corner frequencies, and omega 0 plus or minus 2, same thing, right? Same formulas for both. Okay, so that is okay. I have a problem, an example really. Should we finish this here, or should we do it as part of the problem solving? Which is better? Let's just finish this here, so then we can move on. Again, everything in this slide I just copied straight from another textbook, so it was really not too much effort, but I thought this was good to quickly show you, because the concept of resonance, you have to bring that to the front and understand, and then we can go back to filters. But here, all that we have done is, all that this writer has done is give values for RL and C in a series circuit, and then ask us to calculate all these things. Okay, that's all. So there's no rocket science here. Let's quickly look at it. Given RLC, find the resonant frequency, which is omega 0, the resonant frequency, or the midpoint of the band, and then the half power frequencies, which are omega 1, omega 2. This is how they call it when we are only talking resonance. When we start to move to filters, then we call it the mid frequency, and then we call mid band frequency, and then we call it the corner frequencies. But in resonance, we only use the word resonant frequency and half power frequency. Then we have the quality factor Q to be calculated, bandwidth, beta or B, and then the amplitude of the current at these three frequencies, right? What will be the magnitude of the current? This is here we are interested in current in the RLC circuit. So you just apply the formulas. Omega 0 comes out to be 50. Omega 1, remember, see this formula, it's different from what he just gave on the previous slide. I like this more, it's easier. Directly you can plug in the R and L and C. So you come up with omega 1, 49K, 51K. So this is a narrow band, right? The mid frequency is 50, and the other two frequencies are 49 and 51. Okay. Now, are they related by the geometric relationship? I leave that to you to check. I hope they are. Bandwidth is omega 2 minus omega 1 is 2K radians, as we saw. Bandwidth can also be found as R by L, so he shows you that. Q finally is omega 0 by B, and I'll define that once again, but it's the ratio of the midpoint, the resonant frequency, divided by the bandwidth. So if the bandwidth is large, the Q becomes smaller. The bandwidth is small, it's a narrow band, then the Q goes higher. Okay, so that's the value of Q, or the benefit of understanding Q. Lastly, let's look at what happens to the current, right, which is what we are interested in. At omega 0, it becomes 10, which is because at omega 0, remember, L and C go away, right? We only have R. And at omega equals the corner frequencies, half power, according to the formula somewhere he derived, the currents fall to 70% of the maximum. Okay, so I hope this was beneficial and a good introduction to resonance. Okay, we're done with resonance. We're going to, now that we have understood all those concepts, the rest of the filters business will be pretty quick, because the same ideas are repeated. The same ideas we just read about during resonance, and also some of the ideas we saw for low pass, high pass, all that comes across. Okay, so two examples of band pass filters. So band pass series RLC, band pass parallel RLC. In the case of series, you connect it like this, and the voltage, the value of interest is the output voltage, the value of interest is the input voltage, and so we take the output from the R. Only in this configuration we call it a band pass filter. Okay. Similarly, look at this combination, it's a parallel combination. You might argue that it's a little bit of a series and a parallel, but if you convert this to a current source, then this becomes parallel, a true parallel. So that's why we call it a parallel. So a parallel RLC circuit, also we are taking the output now across this combination of C and L. Only then will this be called a band pass filter. So remember the configurations or the connections and what is the output and what is the input. And he clearly is making the point that together this has one impedance, Z equivalent, which is not the same as the R. Okay, the R is by itself. So these two together make an impedance, and the value of the voltage is across that impedance. Okay. The pictures, the graphs on the left side, you can see, you pretty much know now that there is a center frequency, there is a bandwidth, and there is a half power point or 1 by root 2 voltage drop point, right? And then the phase also starts to drop. The phase is 0 at omega 0, and then it drops from plus 90 towards minus 90 asymptotically. Okay. A few more things here. The magnitude of the transfer function is highest at the center frequency. The center frequency is also known as the resonant frequency, or you can say the resonant frequency is known as the center frequency when we are talking about filters. Q is the quality factor. Higher Q means narrower bandwidth. Okay. All right. What more do we have? A good summary of all the formulas. Now again, a lot of the calculations, derivations are available. Please look at them, try to understand how they are derived. But basically, these are the important equations to know. I guess the first and foremost is you need to know omega 0, the center frequency, and that's a simple root of 1 by LC. The R doesn't appear here, it's just root of 1 over LC. Omega 0 can also be thought of as, the mean of the two corner frequencies. But generally you start with here, then you do a beta, then you start doing these omega C1 and C2, or omega 1 and 1, 2, depending on the textbook. And then you find the Q. There's double formulas for many of these. Which one you use in a problem depends on the context. Important point here, only two of these parameters can be specified independently. That means you can't just say I'm going to pick R, I'm going to pick C, I'm going to pick L, and I'm going to pick a bandwidth and you can solve the problem. No. He's making the point that at best you can pick an R and maybe say, okay, I'll take a bandwidth of so and so, or I can pick a C and I'm going to use a center frequency of so and so. Everything else will start to be calculated based on the two assumed values for the two factors, the two parameters. So be cautious of that. Okay, that was band pass. Are we done? Well, we got parallel. The formulas are slightly different. You can compare the previous slide 26 and this slide. I'm on 27. You'll notice that some formulas are different, not all. Beta is going to be different. Even omega C1, C2 are different. Yeah, so some formulas are different, some are the same. Okay. This is a summary for both types. Series RLC, or parallel RLC, and you can see the transfer function I've tried to pull everything together so when we start doing problems, you can keep coming back to look at this and save time. So you can see how the transfer function in the S domain is written. The transfer function in terms of beta comes out to be similar, same form, but if you don't use beta and you're directly using the R or C values, then the transfer function looks different. So it's better to stick to first calculating beta and then using the same formula for the two. One last variation on this basic idea of bandpass is if you have a source resistance Ri. I don't know why I haven't shown you a picture. I think, okay, it's on the next example slide, but I moved to the next slide, by the way. I moved to 29, and here in this circuit you see a situation where there is an extra resistance attached to the source. Really, it's called the source resistance, and that kind of complicates matters a little bit. So I'm going to go back to slide 28. Remember when we were doing just low pass and high pass, the complication came when we had a load resistance and we had to use some new methods to analyze or new factors such as K. So the same logic applies here, and we bring a K in case there is a series resistance called a source resistance. Okay, so we'll use some of this when we do problems, and hopefully that will help you clear things out in your mind. Okay, I'm moving along to the next slide, which is an example. So we'll come back, some problems, we'll come back later. But I stopped on slide 31. I have to hurry up here because we have some more material. So anyway, I'm on band stop or band reject filters, also called notch filters. So lots of names for this. So what's a band stop filter? A band stop filter is designed to stop or eliminate all frequencies within a band of frequencies. So omega 1 less than omega is less than omega 2. So in this band, we think we have stopped all frequencies. Now clearly, ideally it will be like this square wave where everything is stopped, but in the real world, the actual world, you're never going to stop everything fully, but you will start to attenuate or decrease their magnitude so much that you can say, okay, they don't contribute too much to the output because their power or the magnitude of the gain, the output by input, is dropping towards zero pretty fast. Okay? Now, I guess the picture is clear enough. At omega 0, we dropped. So this entire band between omega 1 and omega 2 is being stopped. The other frequencies below and above are allowed to go through, but the filter stops what's between. And I know I showed you a diagram right in the beginning of this chapter where you saw how the notch works and how the others work. So higher frequencies, lower frequencies go through, mid frequencies stop. Okay, so define this is actually called the frequency of rejection, this omega 0 in the middle. It's the center frequency. Sometimes they still call it center frequency, so don't get confused. But some books like to be a little more fancy and they call it frequency of rejection. But it's still omega 0. Most of the formulas are the same. Here you can see the magnitude of j omega at that frequency is 0 for band stop. And then the bandwidth of rejection, to be more precise, is omega 2 minus omega 1. This probably looks similar to what we already derived. No, it's different actually, yeah. I think, yeah, here we only have beta s on the top for the band pass, but for the band stop, you have s square plus omega square on the top, on the transfer function. Okay, so that was band reject. And how do you implement a band reject? Important question. You take the same RLC circuit, but now you're getting your output across the L and C combination, not the R combination. That's the difference between the band pass and the band stop. Oh, I should call this band stop. Sorry. Okay, so there are again two ways to do a band stop. Actually, there are 1,000 ways, but we are only going to stick to these two. A series and a parallel. And the way the parallel is connected, you now take the output out of the resistance from a parallel circuit and out of the L and C combination in a series circuit. So remember that difference, and then you will know the main difference between the band pass and the band reject. Okay, so here is a summary of all the formulas for a series. How do you find omega 0? How do you find beta? How do you find Q, quality? How do you find omega C1, C2? The formulas are here. Next slide, slide 34. The formulas for a parallel circuit are here. All these are derived in your textbook again, so please take a moment to read that. And then we have the parallel and the series both together in a summary where we see how the transfer functions are written, and they seem pretty similar, but obviously the denominators are different. But if you write them in beta form, then they are identical. Or if you use bandwidth in the formula, then they come out to be identical. Okay, then we have some problems which I will do in the next recording session. So we have another 5 to 10 minutes, and I will talk a little more about active filters. Again, I want to tell you that it's an interesting topic. It's a little more advanced, and I'm sure you will read a lot more as you go into higher classes. I could have totally dropped it in this treatment, but I thought at least I should introduce you. I know some of you are very enthusiastic about op amps and stuff, so you can find one more application of op amps in these next few slides. So that's the secret. If you have an op amp in a filter circuit, it's an active filter. There you go. Okay, so why do we need active filters? Why not be happy with passive? That's because passive has certain limitations, certain features. Number one, they cannot have a gain. So, at most you're going to only get a gain of 1. So, output voltage cannot be higher than input, and that's one limitation. So, you're limited to 0 dB on the gain. Also, they may need expensive and bulky inductors, right? Inductors is the one thing that you cannot make in semiconductor material, and so they can be expensive. They have wires, coils, etc. So they take a lot of room on a circuit. So inductors not very desirable. Number 3, they perform poorly below the audio frequency range. So if your primary application has a lot to do with sound, audio for your music system at home, etc., they're not very good, is what they are saying. But they do very well at very high frequencies, radio frequencies. So there's both good and bad to passive filters. Similarly, the benefits of active filters is that they can have a gain of more than 1. Also, they can be smaller and less expensive because you can do them without inductors. Third, they perform well up to about 100 kilohertz, which is pretty cool, right? Now, certainly not radio frequencies, which are thousands of megahertz, but at least kilohertz, they do very well. Similarly, lastly, important, active filters can be combined with buffer state amplifiers, also called voltage followers, which we talked about when I talked briefly about op amps. Chapter 5, I briefly introduce you to the idea of a voltage follower, which is an op-amp circuit with a gain of 1. And why do we need a gain of 1? And what's the point? It's to provide isolation, very high resistance impedance between two stages, so that one doesn't load the other. So we can eliminate loading effect. So you can create active filters can be combined, and thus it makes it possible to achieve very complex filters. You can have all kinds of filtering for just 10 frequencies here, then you move up, you want another 30 frequencies blocked, and then you go up, and then you have like 1,000 frequencies allowed. All kinds of complicated combinations may be possible by using active filters. Okay, so when you become real filter designers and that's your job, and you're making good salaries as engineers working on filter design, that's where you may be designing such advanced circuits. But for now, I just wanted to let you know that such things exist, and that's why active filters are important. So I will talk briefly only about the low pass filter, active filter in this slide, and really that's about all that I have time for on active filters. Okay. So let's look at this one slide. It's basically the same material, top and bottom, and I'm on slide 39, by the way. So we have the top portion and we have the bottom. The top is from our textbook, the bottom is from another textbook. But basically I wanted to show you that this is how the circuit is drawn. The op-amp circuit, and by now I'm sure you're comfortable and familiar with op-amps and simple circuits at least. So there are two resistors and there's an op-amp and there's a signal on one of the inputs, and the other input can be grounded, and you take the output from one of the pins of the op-amp. Now there is always a feedback resistor, RF or R2, and in the bottom circuit he uses RF and RI, but our textbook they use R2 and R1, which I don't know why, because I know we have always learned it as RF, as the feedback resistor. But anyway, whether it's R2, R1 or RF, RI, you're familiar with the feedback resistor and the input resistor. The new thing that's been introduced is the C, the capacitor. And in fact, we have seen this also. I think we did a very brief look at something called an integrating circuit, I think when we did chapter 6 maybe. So it's the same idea has come back, because the capacitor is a bit of an integrator, right? Anyway, let's not go into integration in calculus, just look at what we have here, which is that the transfer function is written in this form, minus k, and k is called the gain, R2 by R1, which is the gain for an op-amp, an ideal op-amp, you know that. So you multiply that gain with this rest of it, which is what you would have for a low pass filter anyway, right? A passive low pass, omega c by s plus omega c. But you multiply it with the inverted gain, minus k is the passband gain, and you get the transfer function for the op-amp. Okay. Again, I'm not spending too much time with all the detailed analysis, but you can look at it. The same ideas are shown in the bottom, but same terminology. Instead of the k, he writes it here, and instead of the s domain, he puts it in the j domain and moves things around. But this is another way to write the if you're doing some frequency analysis, this is the way to use it. One last thing, the low frequency gain, that means as omega becomes 0, or as we are moving to DC, the gain is just minus RF by RI. But as the frequency starts to increase, you will have slight changes in gain, but until you hit the cutoff, you're okay. You do have some gain, good gain. And how do you get that? You can use this formula. So that's really all I wanted to talk about in detail I have a few more pictures. I'm not even going to talk about this. You can look what a low pass is, a high pass is, how it's connected. Oh, here's band pass. You can see why it's complicated. Band stop, also complicated. How it's built, it definitely needs more than just one op amp. You have to cascade them, and you have a low pass section, you have a high pass section, you have an inverter section. Here you have a low pass section, high pass section, a summing section, and they all add together and they give you your band stop, band pass, which we don't want to spend too much time right now. I have one more example, etc., which we'll look at when we do problems. Okay, so that brings us to the end of the lecture part, and I will catch up again when I start the problems. Okay.